Can everyone hear me? Yeah? OK. These things are not always friendly with people that wear glasses. OK. All right, there we go. All right, awesome. Yeah, it's great to be here. I mean, I live in San Francisco, but it's great to be at React. I was flattered when I was asked to come speak here, and I was asked to come talk about elastic scaling. So that's what I'm going to talk about. So really quickly, who am I? I was a PhD student at Berkeley from about 2007 to 2012. There I started working on a project called Mesos, which Twitter started using in early 2010. I went from Berkeley to Twitter. I was at Twitter for about 4.5 years. I recently left Twitter and am now the chief architect at a new company called Mesosphere. So elasticity and me. So I've worked on components of elasticity for a while. First, when I was a graduate student, I worked on elasticity on multi-core machines, and I'm actually going to talk about that here today. It's actually really fun that I get to talk about that here today. I haven't talked about that work in a long time, and I'm always talking about Mesos, so it's kind of fun to kind of mix it up and come someplace and talk about something else. I also then, of course, started working on elasticity in clusters, which was the Mesos project, and I'll incorporate that into the talk as well, but this talk is not focused on Mesos. So if there's maybe anything that I'd like you to get away from this talk, it's that elasticity is not just about starting and stopping virtual machines. It's an important component of it, but it's not the only thing. So elasticity to me, and the reason why the Mesos project actually got started, was it was about looking at the way that people were statically partitioning their data centers, or just statically creating a bunch of virtual machines in the cloud, and how after they had created that static partition, how effectively they were utilizing the resources that existed in that static partition. And what I mean by that is that most applications have different cycles where they need different amounts of resources. And if you were to actually look at different applications across different times, sorry guys, I'm just going to bend this so when it pops out. OK, everyone can still hear me? Yes? OK. So when you actually look at the resources that are being used by these applications at different time, you realize that if you could elastically move the resources between different applications, you could run those applications more effectively. So rather than running our applications in these static partitions like this, it'd be much nicer if we could elastically move the resources between the different applications. So we could, say, run Hadoop much faster because it could use resources when Rails was not using those resources, so forth and so on. Okay? So elasticity to me, for a long time, has been about utilizing the resources on a single machine as effectively as possible. And as I mentioned, I'm going to talk a little bit about that later in the talk. And that could be between a single application or across multiple applications, multiple tenants. And it's also about across the entire data center, with whatever resources you've already have allocated, how can you effectively move resources between different applications to best run those applications? OK, so that's what elasticity is to me. What is elasticity to Wikipedia? Elasticity to Wikipedia is this quote. And I'm just kind of highlight two of the real important sections of it, which is, it's about provisioning and deprovisioning resources, and it's about doing that in a way which matches the current demand as closely as possible. Okay? I think these are actually really fundamental aspects of elasticity. From the reactive manifesto, what is elasticity from the reactive manifesto? Again, it's this. This is just a snippet that I pulled. And again, I'm going to pull out two little pieces, which is increasing or decreasing the resources allocated and providing relevant live performance metrics or measures, which, as I talk about a little bit later, will be an important part of how we can actually do things elastically. OK, so based on those definitions, I'm going to try to break down elasticity, the what, why, and how, and then set up the rest of the presentation. OK, so what really is elasticity? Fundamentally, elasticity is about being able to allocate or provision and deallocate or deprovision resources dynamically to best match the demand of stuff that's running. Okay? Dynamically means in the order of seconds. Dynamically does not mean submitting a request, 2 seconds later, 3 seconds later, 4 seconds later. Dynamically means in the order of seconds. Okay? Dynamically means in the order of seconds. Dynamically does not mean submitting a request, 2 seconds later, 3 seconds later, 4 seconds later. Dynamically means in the order of seconds. Dynamically does not mean to somebody to go and build a rack or a machine and then install that machine and then using that machine at some later point in time. And best match demand means that we're not over-provisioning our resources. We don't have a bunch of idle resources sitting around. And we're not under-provisioning our resources. We're able to actually meet the demand as best as possible. So that's the what. Okay, so why? Why do we care about elasticity? Why do we care about allocating more resources? Well, first, because if we can allocate more resources, we can decrease the latency for our users or our requests. They spend less time waiting. Or we can increase the throughput. So one of the examples that I showed earlier was having something like Hadoop be able to scale up and use a bunch of available resources that were not being used by Rails. And that means we could actually process our Hadoop jobs even faster. Okay? Why deallocate? Well, because we could let somebody else use the resources. Rather than holding on to them and keeping them idle, we could deallocate and let somebody else take advantage of them. Or we can save money. Because if we're in a private data center, we might be able to turn off machines. If we're in a public data center, we can actually kill our virtual machines, and we can only pay for what we use. Okay? So the mechanics of how are some of the more complicated bits of elasticity. But at a high level, elasticity is really about scale up or scale down, which is what most people call vertical scaling, and it happens on a single machine. It's either adding more resources to that single machine or adding more resources to the applications that are running on these individual machines. Okay? And scale out or versus scale in is now about running across multiple machines and what most people call horizontal scaling. Okay? There's a lot more details in the how, though. The first is, okay, so how do I actually write software that can scale up, scale down, scale out, and scale in? Another big question of the how is, how do I actually allocate and deallocate resources to this software? What's the process? How does that work? And the last one is, how do I actually optimize the allocations so that I can do that part that's really important about elasticity, but best match the demands of my applications and my users? Okay? So these three questions I'm going to return to throughout the talk as we talk about the individual pieces. Okay, so in the rest of the talk, I'm going to talk about scale up, scale down first. Because to really understand how you can do elasticity in a scale out, scale in way, you really need to understand how we can do elasticity in scale up, scale down on a single machine. Okay. Then I'm going to talk about scale out, scale in. Then I'm going to incorporate Mesos, and specifically how Mesos was built to help it easier to build elastic applications. Then finally, I'm going to conclude. Okay. Okay, so jumping in scale up, scale down. So most people, when they hear the words elasticity, they associate it with cloud computing. And most people associate cloud computing with distributed systems. Therefore, most people associate elasticity with distributed systems. But really, elasticity is just about this fundamental what and why, which is I want to allocate and deallocate resources dynamically, and I want to do it to decrease latency or increase my throughput. Okay? So there are a lot of applications that if you just looked at this definition, you can say, oh, well, that's an elastic application if I sort of thought about it in that way, if I had an elastic perspective for how I actually built my applications. So a standard application that I'm sure many of us have written is a web app. And if we took an elastic perspective to the web app, whenever you got a new request, you'd create a thread. When the request's completed, you destroy the thread. And this is a very elastic thing, right? We're allocating more CPU whenever we allocate the thread. Of course, even on a single core machine, even allocating more threads means there's time slices we might be able to take advantage of because the threads might be blocking if we're not using non-blocking functionality. And the scale down part is when when the thread completes, we actually deallocate that thread so those resources can be available for something else. Okay? Okay, so the systems we've been writing all are elastic, but what most of you are probably thinking in the crowd is, okay, that's great, it might be elastic, but it's definitely not scalable, right? I can't write a thread per request service, I can't make that scale, even though Ben said in his last talk that Netflix is still making it scale. Okay, so the key word here is really scalable, right? A thread per request is not scalable. So this really, whoops, there we go. The keyword here is really scalable, yeah. So this really makes us want to understand the positioning of what it means to be an elastic service versus what it means to actually be a scalability service. So really quickly, scalability, as I use it throughout the rest of this talk, I'm referring to the degree in which the performance of the system improves after adding more resources, okay? So that's what I'm describing as scalability. And a scalable system is one where performance improves proportionally to the capacity of resources added, right? So if I put this many resources in and my performance improves like this, and the next time I put this many resources in and it improves exactly the same, and it's proportional, that's a scalable system, okay? So scalability is a prerequisite for elasticity. If we want to actually build elastic systems, we have to build systems which have some notions of scalability. Now, this doesn't mean that it has to be scalable. It just means that you can have diminishing returns. It just means that if we put more resources into the system, we have to be able to take advantage of those resources, okay? Otherwise, what's the point of actually allocating more resources? So, so that implies that we need to actually think about what it takes to build scalable systems if we actually want to run them in an elastic way. So, getting back to our original thread per request, since that was not scalable, what's it going to take to get to software that ultimately is scalable? So, this is sort of a fun graph I just pulled. I actually pulled this slide from a lecture I'd given when I was a graduate student as a TA at Berkeley, which is kind of fun to be able to pull it out again. Okay, so over time we started with the thread per request model that had lots of bad properties. Ultimately we moved to thread pools, typically bounded thread pools. At the same time, a lot of people stopped using threads. They started working with things like event-driven. Again, we're trying to drive towards things that are more scalable. There was this really interesting work where there was this merging of this notion of both thread pools and event-driven. The architecture there was called staged event-driven. How many people have heard of staged event-driven architectures? Okay, cool. So I'm going to use it as an example throughout the talk to really explain how to build scalable systems. So, and then this is some new slides that I actually added. From stage event-driven, there were other similar work that are not derivations of staged event-driven, but they're related. The two that I kind of really want to highlight are actors and the disruptor pattern. Again, actors existed far before stage event-driven, so this is not a derivation. This is just how people are actually using these technologies. A lot more people are using actors instead of something like a stage event-driven architecture or something like the disruptor. Okay, so as I mentioned, I'm actually going to use the stage event-driven architecture to really describe and to really expand on what it means to build one of these scalable systems. Okay, so what is the staged event-driven architecture? So this is a picture actually taken from Matt Welsh's paper where he describes SATA. And basically, from 10,000 feet, the staged event-driven architecture is a collection of stages where each stage has a thread pool and a collection of queues. And the way that this works is that processing happens in thread pools in each stage, and after some processing has been done, it outputs an event, and it passes that event to some other stage, which gets queued up in that stage's queue. Okay? So what's really interesting about this design? Like, why am I spending any time talking about this thing? So the stage approach leads you to a couple of very nice properties about your software. First, you end up building isolated stages. Okay? And as we find out later, building isolated stages is going to make it easier to replicate those stages. All right? You end up building these things in loosely coupled ways. There's actually interfaces between these stages. Those interfaces, strictly speaking, are actually queues. And it becomes much easier to maintain your software because you focus on individual stages, and you can just think about that stage. Pat's talk this morning, when he was ending his talk, he was talking about, all you really have to care about is the API you're working with this software. You don't need to care about anything else. It's very similar here. When you have this nice notion of being able to be behind an API, and these systems are smaller, and you loosely couple them together, you can just focus on your individual stage or component, which makes it much easier to debug, to reason about, so forth, so on. And the last bit is these stages become composable by nature. That's how you actually have to hook these things together. That makes it easier to reason about. Okay, so what's really nice about this stage approach and what this is really forcing people to think about is a unit of scalability. Is this thing that I build that I can then replicate and scale up, scale down, scale out, or scale in, okay? And in fact, even in Stata itself, there's this notion of the thread pools are actually dynamic. They actually do scale up and scale down in the thread pools based on the amount of resources that are required for each individual stage, okay? But the other thing that this really gives us is it gives us a building block for concurrency. You know, I can replicate these things, I can build these things, and then I can go from there. And you know, when I started to think about how I wanted to kind of talk about concurrency in this talk, and specifically how it relates to parallelism, I decided that the right way to do it was to really just explain concurrency and parallelism based on the way Rob Pike explains concurrency and parallelism, because I think that he's got it really, really right. Right? So in concurrency, the goal is not actually to run things in parallel, but the goal is actually to think about what it takes to have a good structure to your software. Okay? Where good structure means it's composable, it's easy to reason about, it's easy to debug, so forth and so on. It's easy to hook together. Versus parallelism, the goal is actually simultaneous execution. The goal is actually, I want to run these things in parallel. The goal is actually, I want to do things in a scalable way. I want to run more of them, and I want that to actually work. Okay? So what I think is really interesting about the juxtaposition between these two is that good structure, having a model that has good concurrency structure, is something that's really necessary to be able to actually run these things in parallel. Okay? It's not the goal, but if you don't have good structure, it makes it incredibly hard to actually execute that software in parallel. But good structure in itself is not sufficient. Just because you have something which gives you a good structure doesn't necessarily mean that you can run that thing in a scalable way. Okay? And going back to the example I started with, which is threads per request, I'll argue that threads are a great structure. Okay? Now, this is blasphemy because Mesos is actually an actor and completely message-passing based model. But I'll argue that threads are a good structure because we can easily explain them to somebody from the very beginning, and they can get something. They can get some kind of concurrency and parallelism to start. It's easy to reason about. I think somebody earlier today, maybe it was Martin, was saying that yeah, threads are great when you first start, but when you start to actually scale those and get them to many threads or many services interacting with threads, then it becomes nearly impossible to reason about. But to start, it's a very easy model to reason about. Okay, but threads are hard to scale, right? That's getting back to this whole thing. Threads are hard to scale. So why are threads actually hard to scale? Threads are hard to scale because they encourage, as programmers, us to write software with bad practices. For example, to use things like shared resources, to use things like locks, to use things like mutable data. Okay? So I've got a few slides about shared resources, but I thought for fun, a couple days ago when I was actually thinking about shared resources and how I would want to put this in the talk, I thought I would write a little haiku. So I wrote the scalability haiku, okay? And it goes like this. So it's 757, okay? So it's avoid all shared resources, but if you cannot, try to batch and never block. Okay, so that's my scalability haiku, okay? Yeah, it's good. Okay, so why are shared resources a bad pattern? Well, first, what are shared resources? So I'm talking about things like disk, network, other devices which we might need to share. I'm talking about things like mutable data, and in particular, the locks that we're trying to actually acquire to manipulate that mutable data. But I'm also talking about other resources we use to do computation, like CPU and memory, too. Okay? So why are shared resources, why do we want to avoid shared resources? Because number one, because shared resources cause you to have contention, and contention causes you to wait. Okay, so you want to avoid shared resources because you're going to contend for those resources, and then many things are going to wait. Okay, so this is, by the way, this is supposed to now be getting back to the haiku. Okay, so you wait. Okay, so blocking. So why don't we block? So we don't want to block because if we block, we're going to ask the kernel to actually completely context switch us out and context switch something else in, which is extremely expensive. And it's far more likely that we could have done something much more effective with the CPU time doing all that context switching if we would have just not blocked and said, okay, well, I can't do this right now. I'll do that thing later, and I'll use my resources to do something else. So I know that Martin has this notion of mechanical sympathy. I'm calling this kernel sympathy. You should be sympathetic with the fact that, that the kernel here is, yeah, it's not, context switching is not in your best interest. So, and then batching. So why would you want to do something like batching on shared resources? So because batching really enables you to do more at once the contention has been resolved and you've actually waited. And again, I think that Martin probably said this best earlier, but batching is not just about putting a bunch of things in and then when a certain time evolves going from there. It's about trying to saturate the underlying device as much as possible, whether it be the bandwidth, whatever it is. It's trying to take advantage of that device as efficiently as possible. Okay? So avoid shared resources. Now, there's this special case of mutable data, which is a shared resource, right? But it's a special case because it's not only a contention point, it's not only a shared thing that you want to avoid, but given the architectures that we actually run on today, it also requires us to do some kind of coherency to make sure that when that data gets updated, other things in the system is notified and can actually act on that data. Okay? And so this is just a quick picture of a NUMA node and the reality of what it means today to be manipulating mutable data. And this kind of gets back to the universal scalability law, and in particular that the two of the biggest things that really hurt you with scalability is contention, which you've already talked about, but the other big one is coherency if you actually want to scale. Okay, all right. So getting back to SATA. So what does this all mean for SATA? Well, SATA gives us a nice concurrency model, but it still means that when we build this thing, we need to make each of the stages themselves share nothing. If we want this thing to scale, we still need to make these things share nothing. It's a good model, it's a good structure to start with, but it's not sufficient. We have to go the extra step as well. Okay? Now, at the end of the day, some things still have to be shared, right? At the end of the day, you still need to share things like CPU. There's plenty of resources that you still need to share. And so what I wanted to do was I wanted to take a little bit of time to talk about how we share and specifically allocate resources of something like CPU in just a parallel system and how that relates to elasticity. Okay? So getting back to this slide that I talked about earlier, you know, we've talked a lot about what it takes to actually build software that can scale, the things you need to do to build software that scales. And now I want to talk a little bit about how you can actually allocate and deallocate the resources. In particular, I'm going to focus on CPU on a single machine in an elastic way. Okay? All right. So sharing CPUs. So if we look at one of these individual stages, we have a couple options. So we've got threads that we're allocating for each of these stages. Threads are backed by CPUs. CPUs are a shared resource. This is a point of contention. We have to figure out how we actually want to use these things. Okay? So we kind of have two options. The first option is we could allocate way too many threads per stage, okay, which oversubscribes the CPUs, which obviously leads to the contention I was just talking about, which causes thrashing, and thrashing ultimately hinders our scalability. Okay, so we probably don't want to do that. We probably don't want to do some sort of elastic approach where we allocate way too many resources. On the flip side, we might allocate far too many threads per stage, which might leave CPUs idle, which could significantly limit our performance, which could increase the latency of our users trying to get stuff back or decrease our ultimate throughput. Okay? Okay, so that's kind of directly coming from SATA. I'm going to kind of transfer a little bit to an actual parallel system that we actually did some really interesting elasticity work with, specifically in the realm of what's the best way to share CPUs elastically between an application that's run at the same time. Okay, so the example is for sparse QR factorization. So has anyone heard of sparse QR factorization? Not really? Okay. I won't ask you if you've written it then. So what is sparse QR factorization? Well, it's a bunch of math. It's some software that's doing a bunch of math, so we won't even talk about that. What we will talk about, we will talk about, though, is what sparse QR factorization looks like in a programming sense, okay? So we've got this program, SPQR, and what it does is, the first thing it does is it creates a bunch of tasks. So So it's trying to do a bunch of math on a bunch of basically vectors or matrices. And at first, it breaks those matrices into a whole bunch of different tasks that it can run in parallel. Okay, so that's the first step. The second step is that each one of those tasks then tries to call into the MKL, the math kernel library, which is a library from Intel in order to do some math on the actual matrices that you have, okay? And the math kernel library itself is actually implemented as a parallel system, okay? So one way to think, oh, and then this happens for all these tasks, okay? So one way to think about this is there's many different stages that are working at the same time, and you're passing information between those stages. One of the stages is the first stage, which in the software that I'm actually referring to was implemented using TBB, which is Intel's threading building blocks, which is an abstraction that makes it easier to create something like a queue of tasks that you actually want to run in parallel, and OpenMP, which is another way of actually doing parallelization of some software. It's a different model. It's more like the fork join model, whereas TBB is more like the work queue model. Okay. And so the big question that we have when we're building a system like this is what's the best way to allocate CPUs, resources in general, but specifically for this example, CPUs between these different stages, between these different components of the system, which are actually completely shared nothing. They're not sharing anything at all whatsoever. The only thing they're really sharing at the end of the day is CPU. Okay? And specifically, how many CPUs or threads do we want to allocate between these different stages? So literally what I mean by that is, do we want to only give something like TBB 2 threads or 2 cores or 2 CPUs worth of resources to actually run its parallel computations? Or do we want to give something like, on an 8-core machine, the rest of the cores 8? Or do we want to give something like TBB 8 cores and something like OpenMP 8 cores or 16 cores or whatever it is? What do we actually want to do for this system? Okay, so here's some pretty interesting graphs. So this is a 16 core machine. Okay, and what we've actually done for this program is we've run all possible permutations of how many cores basically we give to each of the different stages. Okay, so we say okay, we're going to give so in this corner. This is giving 16 cores and 16 cores, so they're completely competing for resources. And in this corner over here, we're giving basically no cores and no cores. Okay? Lower is better. So over here, it's a bit more expensive. The minimum is like somewhere over here. It's not actually 8, 8. The right thing to do is not to give 8 cores to OpenMP and 8 cores to TBB. I forget exactly what the optimal was for this manual configuration, but I think it's something like 4 and 8, or that doesn't equal 16, 4 and 12 or something like that. Okay? All right, so this is just runtime of the actual application. All right, here's L2 cache misses for that exact same application. The same experiment that was run, except now we're showing cache misses. Okay? And as you can see in this case, when we start to add significantly more CPUs, when we start to oversubscribe the CPUs, the number of cache misses along this side get significantly higher. They get much, much higher. Okay? And then this last graph is the number of context switches. So the number of times that threads actually are getting context switched in and out. And again, there's this general trend towards when you're running when you're oversubscribing the CPUs more, there's a lot more context switches that are happening. Okay? So what's the solution to this problem? There's probably many solutions, but what's the solution that we actually worked on that was really interesting? It was to do things elastically, which is great, because that's what I came here to talk about, elasticity. So what does that mean? Well, what it means is that why don't we dynamically allocate the number of CPUs between these different stages over the course of the application actually running, rather than starting with some fixed allocation or trying all possible permutations in the space and then saying, oh, the best I got was 12 and 4, so I'm going to run my application always with 12 and 4. Why don't, when I need to run the application with 2 and 6, or is that 6? Yeah. I'll run it with 2 and 6, and when I need to run the applications with 4 and 4, I can run it with 4 and 4. When I want to run it with 5 and 3, I can run it with 5 and 3. hey, sometimes I might want to run it with just 1 and 7, right? So why don't I dynamically allocate the CPUs across, okay? So the point of this is that we can match the demand of the application, the amount of computation it has to do, as closely as possible with the resources that we're actually allocating to it. So I'm going to kind of walk back through these slides because they're interesting. This gray box at the bottom, that's what happens when we dynamically allocate the resources between the different stages at the same time. So it's significantly lower than any of the points that we try to manually figure out ourselves. So here's this gray box again, this gray plane again, significantly lower. And then the final one is this one. And what's interesting here is that the number of context switches, when you start to get into some of these oversubscribed territories, is an order of magnitude greater than the number of context switches when you actually dynamically allocate the resources between the two. Okay, so I hope you found this interesting. This, to me, is exactly the kind of area that we want to focus on when it comes to elasticity. We did write a paper about this in 2010. It was in PLDI. If you want to check it out, I think the slides will be available, and you can come back and check it out. Okay, so the takeaway from this whole section. You need to make the software scalable to make it elastic, okay? At least if you want to have any value of running your elastic software. There's lots of ways in which you actually want to build scalable software. And then the other takeaway really is that elasticity becomes especially valuable when resources become constrained or sparse. So it's not just about allocating another virtual machine, but given the resources that I currently have, what's the best way that I can elastically take advantage of those resources so I don't oversubscribe and I don't undersubscribe? Okay? And as I'm going to talk about a little bit later in the talk, resources are always constrained. There's some resource that's always going to be constrained. Okay? Okay. Cool. So I'm going to transition now to talking about on a single machine, elasticity and scalability on a single machine, and specifically scale up and scale down of resources on a single machine. And I'm going to go on to talking about scale out and scale in. Okay, so what's scale out, scale in? Well, it's just, instead of doing all this on a single machine, we're going to actually do it across multiple machines. All right. So I think one of the most interesting parts, and it's been echoed in a few other talks as well, is we've already done this. We're basically already scale out. If you look at our architectures that we run on today, they're effectively scale-out architectures. They're effectively a bunch of machines all connected by some kind of a network, okay? Which is one of the reasons why there's a ton of value in building in the way that you build your distributed systems to be exactly the same in the way that you actually build your parallel systems, because the architectures are very, very similar. Okay? And if you do it that way, if you actually build your parallel systems and your distributed systems in the same way, then when you want to actually scale out, it's as easy as just stamping out new instances of your application. You can just launch more applications. They all work in the same way. Everything's great. So this is again, going back to SATA, all we have to do is take these stages, and we can just go from there. So one of the things I neglected to mention earlier is if you don't want to use something like SATA or stages, you can replace this with something like an actor, right? So you can just take those actors, you can stamp those out, you can run more of those actors. All right. So it is true that we're already basically running. We should already basically be building scale-out applications, but there are differences, right? So the first biggest difference is that it's a tremendously difference in order of magnitude when it comes to the latencies that you'll see on a single machine across multiple machines, right? So for scale-out, it's even more important that we focus on share nothing. It's even more important, okay? Similarly, the other big difference in scale out is now we have to start dealing with failures. There's not too many of us, if any of us, that build parallel systems and ever assume that one of the Newman nodes may fail. We're really not there yet as an industry. Maybe at some place we'll actually get there. But when you actually want to start doing things in a scale-out way, you need to actually incorporate that into your software as well. Okay? So stuff can actually fail. So what does that mean? Well, that's not a big deal if stuff actually fails. It is a big deal if you need to make sure that the state or the data that thing is controlling needs to get replicated. And so there's this interesting interplay where, yeah, you might have something that you can stamp out, that you can scale out, But because of failures, it often forces you to think about how you need to share some data between these different things that you're actually stamping out. Okay, and again, since we're at a different order of magnitude, the consistency or the coherency of the actual updates of those data becomes especially more expensive. Okay, so very briefly, this is not part of my talk at all whatsoever. I just kind of wanted to throw it up there, and it's been talked about in a few of the other presentations as well. There are definitely options to do. To get your software to scale in a scale-out-like environment. When it comes to consistency and coherence, you can start making your consistency be eventual. That might be cheating yourself, depending on the actual application that you're running. And there's a lot of other interesting data structures that you can take advantage of as well. CRDTs, which I know was chatted about earlier with Pat, so I'm not going to go into them in any detail. And then things like append-only replicated logs. Different ways of actually working with this data that might need to get shared between multiple of these components that you've scaled out. Okay, so scale out at Twitter. So this is maybe the other reason why this is interesting topic for me to talk about. This was Twitter in circa 2010 when I joined the company. It was a one giant monolithic Ruby on Rails app that we affectionately dubbed the monorail. And it pretty much did everything except for storage. Okay? And it had a lot of this, which I'm sure many of you often saw. So what did we actually do, right? Well, we said, all right, well, we can't have this monolithic structure. We need to have a structure. We can have a bunch of individual things that are isolated, that are loosely coupled, and that are composable, just like we want to do with the SATA-based architecture, so that we can scale that out across our data center. And that's exactly what we did. In 2010, we started changing the company from being a monolithic Ruby on Rails app to something that looks like this, that people more traditionally call a service-oriented architecture. We have a bunch of microservices. Okay? In particular, one of the things I want to highlight about the core services in the center is that they're all stateless. Right? So that those same principles of you got to share nothing on a single physical machine, those same principles apply here as well. We want to share as little as possible. We want them to be stateless. So there's no data coherence or consistency. Okay, so as I mentioned again, if you squint, something like SATA actually starts to look like a service-oriented architecture. Okay. All right, so getting back to the slide, how do we write software that scales? I want to spend a couple of slides and talk about how we actually allocate and deallocate resources in a cloud-like environment. I've talked about how we actually allocate and deallocate resources on a single machine. You just do something like pthread create or memallocate, and if you can get the resources, you get the resources, and if you can't, you don't. Okay? In a scale-out-like environment, it's a little bit different. Okay? So first I'm going to talk about it from the perspective of most people run on the cloud, and then I'm going to transition a bit and talk about what it looks like in a place like Twitter. Okay? So the state of the art, really, in the cloud is you run a bunch of instances. You have those instances report metrics. This gets back to the Reactive Manifesto's definition of what it means to be elastic. You have them report metrics, measurable things. Those metrics get reported to something like Amazon CloudWatch. CloudWatch can then use that information based on some rules you can set up to decide when you might want to launch more virtual machines, okay? Or when you might want to actually destroy virtual machines. Based on certain metrics, you'll take one of the two options, okay? So this is fine, but for our purposes, at a place like Twitter, the state of the art is kind of unsatisfactory. First, we can't just arbitrarily launch virtual machines, right? We're in a private data center. So we can't actually do something like that. But more importantly to us, we wouldn't necessarily want to just launch a virtual machine because oftentimes the unit of scalability, the next thing that we're actually launching, rarely equals the size of a machine. It rarely is, oh, I need to scale this up and I need an entire machine's worth of resources. Much more often it's, oh, I just need a couple resources that would fit somewhere on some machine. Okay? So as I'm going to talk about it in a second, rather than actually wasting productivity trying to build your software to be right-sized for particular machines, why couldn't instead we build software that just could harvest all the available resources, and when we wanted to elastically scale out or scale in, we can just use those resources for running our tasks. Okay? And that's actually where Mesos enters the picture, and so I'm going to chat a little bit about Mesos. Okay? Okay. So from, I guess, let's see, from 10,000 feet, I suppose, what Mesos is it's really a distributed system for building and running other distributed systems. Kind of a weird way of describing it. Another way, though, is that it's infrastructure, specifically relevant for this talk, it's infrastructure that makes it easier to build elastic distributed systems. Okay? So what do I mean by that? Well, the way in which we build and run most of our distributed systems in the past looks something like this. What we actually do is we say, okay, this fixed chunk of resources we're going to give to this distributed system, and this other fixed chunk of resources we're going to give to this other distributed system, and we're going to actually describe that as just a bunch of machines. These machines are allocated for this system, these machines are allocated for this other system. Okay? So an elasticity event in that world, what it looks like is we go and we allocate or provision an entire other machine, and then once we've done that, we say to the system, hey, this machine is now available for you to use. We pass it over to that machine, and then it uses it. Okay? So what are we doing in Mesos? What's the fundamental difference between the way that you would actually run your distributed system before Mesos to after Mesos? So the fundamental difference is that the applications themselves, rather than just being managed by humans and deciding what machines are part of that application's pool of resources, the applications themselves are working with software to get resources allocated to them. Okay? So these coordinators now do not just have machines that are pre-allocated, statically allocated towards them. Instead, they're working with Mesos directly, and Mesos ends up being this level of indirection, which makes it very, very easy for us to elastically allocate and deallocate resources between the different applications that are running on top. Okay? So, so the example I have, well, first, the joke I often make in my talks, and I have to make it here too, is you solve all problems in computer science with a level of indirection, and this is what we're trying to do here. We're trying to stick a level of indirection between the actual machines or the resources and the applications that are trying to run computations so we can elastically share the resources across the applications. Okay, so already what this starts to let us do is that allocation of resources that I showed earlier could start like this, but now very, very dynamically, we can change those allocations without having to get a human involved based on how best we want to meet the current demands of the system. Okay, and this stuff can iterate back and forth. Okay, so we've already seen this slide, but this is what this system is exactly trying to do. When Rails is not using those resources, it can give them to Hadoop to actually take advantage of those resources. Okay, all right. So what are the big benefits of Mesos? Well, one, the software ends up being the thing that's responsible for actually requesting the resources, for making the requests, which is a really, really interesting paradigm when you think about it, because most of the way that we end up setting up our elasticity in the cloud world is that there's some other software, something like Amazon CloudWatch or some other software that we ended up building that ends up watching the software and then deciding when it might want to elastically scale up or scale down. In many cases, the programmer that's actually writing the metrics that would know when it would want to scale up or scale down could just ask that directly. And there's a lot of examples of that, things like Spark, Hadoop, and Jenkins. It knows when it has more jobs. It knows when it would like to get those resources allocated to it so it could actually run those jobs more quickly. Okay? And then the other big advantage here is that the resources that get allocated don't have to get allocated at the level of virtual machines. The resources can actually get allocated at the granularity of whatever size resource you actually need for the task that you're running. Okay? So in Mesos, we've been allocating resources like this for a long time. We've been sticking them inside of containers And that's kind of the lightweight mechanism where we can still get the isolation, but not have to allocate you an entire virtual machine with its own instance of the operating system every time that you want to sort of scale up with a new task. Okay? So we can actually make that allocation from order seconds to order milliseconds. We can launch your tasks in milliseconds instead of seconds, provided there are available resources. When there's not available resources, we can provision more machines. Okay. All right. All right. So this is a couple of the examples of the applications we've actually built on Mesos. Spark, Hadoop, Jenkins. There's a whole bunch of other ones. One I want to highlight is actually Apache Aurora. This was one of the applications that we built on Mesos for running all those stateless services that I showed in a previous graph. So rather than requiring all people that are writing applications to have to request their own resources through code, even though one day we might actually get there, we built sort of this in-between framework, which made it really easy to say, hey, just run this service, this many instances of it, and go. Okay? And Apache Aurora is what actually runs all services on top of Mesos, is what runs all stateless services at Mesos today. Okay. So just a couple more slides on Mesos, and then I've got a few more slides, and then I'll wrap it up, take some questions. There's been a bunch of things that have been built on Mesos over the years. Again, this isn't a Mesos talk, but I figured I'd throw this in there nonetheless. There's also been a bunch of things that have been ported to run directly on Mesos to leverage this API to be able to elastically use resources, things like Hadoop, things like Storm, that's the lightning bolt logo I'm using, things like Jenkins. And we've had a bunch of adopters that have actually started using the technology. Twitter obviously being one of the biggest, but also Airbnb, HubSpot, OpenTable, eBay, Groupon, and Netflix. There's other companies as well. I just listed the ones that I've had some kind of a personal relationship with. Okay, so a couple more slides on elasticity, because I think one of the common beliefs in elasticity is it's this notion of you have infinite resources, right? Elasticity and infinite resources. This is like the wonderful part about cloud computing. I can just always allocate more resources to run my applications. Well, in the real world, there's constraints, right? If you're running in a private data center, I can't just quickly go allocate another machine, but it doesn't mean that the ideas behind elasticity aren't still very relevant for me and still very useful, right? I'm not going to be able to provision another machine, but I can still elastically move resources across applications that are running at the same time, and that's precisely what we use Mesos for at Twitter. There's another really big constraint, though, which is money. At some point in time, you still can't buy any more virtual machines. And at that point in time, you want to figure out what's the most effective way that you can leverage those virtual machines across all the applications that you're actually running. Okay? So there's still some constraint at the end of the day, and you'd still like to be able to use those virtual machines in the best way possible. So I think one of the areas of elasticity that will sort of grow a lot in the near term is building elasticity algorithms that are trying to match demand as closely as possible, but in constrained settings. When you can't just go launch another virtual machine, when you want to best take advantage of whatever resources you have today. And I think what's interesting about that world is success is going to look differently to different companies. To some companies, they're going to want to do the best elasticity allocation algorithm because they're going to want to drive up throughput. And in other companies, they're going to want to do something that's going to allow them to make the most money possible, which might mean that actually certain users have poor experiences, but they've decided to elastically move the resources to something else because that's the thing that's actually going to be making them the most money. And to do something like that, you really need to actually have this infrastructure in place where you can start actually allocating and deallocating the resources very dynamically across the applications. And that's one of the big wins of having something like Mesos running in your data center. Okay. So I'm just going to conclude real quick. So some parting thoughts. Scalability. Scale out or scale up. The principles are exactly the same. You need to use good structures that are conducive to actually scaling, but that's not enough. You still need to build your software to, as much as possible, share nothing. Elasticity is it's more than just adding and removing resources. It's also about making the best use of those resources that you already have allocated, and constraints are a reality, so we actually have to work in that. So another conclusion I want to make, when I was first talking about possibly coming and giving a talk here, I was thinking more about talking about how Mesos itself is a reactive piece of software, and I kind of wanted to end talking about this because it's really interesting. Mesos itself is actually, it's an actor-based system. It's based on message passing with an asynchronous event loop under the covers. You can go check out Mesos at the link here. We actually have an implementation of multi-Paxos, a multi-Paxos-based replicated log that was built in 2009 with batching. Which is pretty cool. And I guess the coolest part about all of these things is that this is all in C++. So there's a few there. OK, all right, so I've spoken for my 15 minutes, and I'm happy to take some questions. Yeah, so for stateful services, that's the next slide. Yeah, so how do we actually do things in an elastic way for stateful services? So I do have some more slides, but I'll just kind of talk about them out loud. So what I think is really interesting about elasticity for stateful services is that a lot of stateful services, you could take resources away from them. You just need to do it in a way where they understand that the resources are being taken away. You need to basically prep them with the fact that resources are going away. Right? So one of the things that we're building into Mesos directly is this notion of if you're running a stateful service on Mesos, and we want to, say, take some resources away from it because whatever allocation algorithm we're running has decided that this service should not have this many resources, and we want to take that stuff away, we can bound, we can give the service some bounded time and say, you need to get off of these resources within this amount of time, and it gives the service some opportunity to do something smart, like, for example, restart replicating some of that data and some of the other shards that it has, whatever else it wants to do. Okay? So the example I like to give from actual operating systems is operating systems should do this for applications that are running on my laptop and on my servers today as well, and they don't. Instead, what they do is they pick something like LRU, and they say, when I've decided I'm going to page you out to memory, I'm going to take you the least recently used memory page, and I'm going to write that thing out to disk. It'd be much better if instead it said to the application, what's the memory block you'd like me to write out to disk? Because I need to free up this page. I'm deallocating resources from you, where to go from there. So the same principles are principles that we're actually applying in Mesos as well. So you can run things like stateful services. They can find out when the resources are to be taken away, and then they can continue executing. Yep.
How do you dynamically figure out how to shuffle the CPUs around for like a process?
In the previous work I was talking about on a single machine?
Yeah, where you have the two different threads and you want to figure out how many CPUs to get to each sort of task.
Yeah.
How do you do that in runtime?
Yeah, so that's exactly what the entire Lithe paper is about. And from 10,000 feet, it's basically about the software itself, the libraries themselves, TBB and OpenMP, determining the amount of resources that they believe they need right at that point in time, making those resource allocations, and then maybe or maybe not getting those resources allocated to them based on some higher level scheduler algorithm, which is actually trying to decide what's the optimal thing, what's the thing you're trying to optimize for. Are you trying to optimize for the first part of the path, the first stages, TBB running stuff more effectively, the other stages? The graph that I showed was actually first come, first serve. The planes that I showed was first come, first serve. It was doing nothing more than just eliminating the contention on the CPUs. That's all it was doing, which sort of shows you how much that was just low-hanging fruit, right? There's a bunch of other graphs that we talk about in the paper as well, where we tweak that around and we try to do smarter things, and we can get even better performance when we try to actually allocate based on certain goals that we have, like optimizing OpenMP's performance or optimizing the number of L2 cache misses or optimizing the number of context switches. OK. Any other questions? All right, thank you so much.